Welcome to the lecture series on soft computing in computer science. Today's lecture is going to talk about fuzzy relation. Before introducing the topic fuzzy relation, let me recall few ideas behind fuzzy sets and operations. As I said in the previous lecture, the concept of fuzzy set is a idea that is derived from multi-valued logic, where it is used to represent the linguistic information of any languages. How to process those linguistic information via computers. The next important phase followed by fuzzy sets and operation is fuzzy relation. Of course, this topic is also related with classical relation, and then we slowly migrated towards the idea of how it is related with fuzzy relation. First of all, we should know what is a relation. A relation is a mapping or pairing of input values with output values. So, you have set of input values and you have set of output values, and the set of input values are called domain and the set of output values are called range, right. So, here you have lot of points and here you have lot of points, right, and each point in the domain is mapped to each point in the range. And if it is mapped like this, then it is said to have a relation is existing between two entities, that is input and output entity. Strictly speaking, it is domain and range. And this relation is viewed or can be termed as a function. Suppose if at least one input has more than one output, then the relation cannot be viewed as a function. Let us see how it is. See, identify the domain and the range, then tell if the relation is a function or not. I have a set of inputs and I have a set of outputs, right. In the input side, I have -3, 1, 4, that is domain. In the output side, I have 3, -2, 1, 4, that is range. Now, I wish to try to map these two things. So, 3 is mapped to +3, -3 is mapped to +3 and 1 is mapped to -2 and 1. So, if you could see that this relation cannot be expressed as a function. Why? Because input 1 is mapped onto both -1 and 2. So, in that situation, this kind of relation, even though there is a relation exists between input and output, that is a domain and range, this cannot be treated as a function. Let me take one more example, right. So, here I have some set of input values -3, 1, 3, 4 and I have some set of output values 3, 1, 2, -2. -3 is mapped to 3, 1 is mapped to 1, 3 is mapped to 1 and 4 is mapped to -2. Whether this relation can be expressed as a function? Yes, of course, this relation can be expressed as a function. Why? Because each input, if you could see that each input is mapped to a output, that means exactly one output. So, that is the situation or that is the condition that a relation can be expressed as a function. In the previous case, this is not possible because one input is mapped to two output. But here each and every input is mapped to each and every output. Of course, these two inputs can have same output, but no single input can have two output. So, that is the condition. So, if a single input is having two output, that is it is mapped to two output, then it cannot be represented as a function. Rather than if more than one input, if it is mapped to a single output, that is exactly one output, then it can be mapped as a function. How to represent that relation using a function? The relation is expressed as a function by means of ordered set of pairs. Let us take an example. X set of input and Y set of output. We have the pair of values -3, 3, 1, -2, 1, 1, 4, 4. So many functions can be represented by an equation in two variable form. Say for example, see y equal to 2x minus 7. So for which if an ordered pair is given is a solution, and if that equation is true for the value of x and y that can be substituted into this equation, then we may say that this can be represented in the form of a function. In this particular equation, these input variables are called independent variables and the output variable is called dependent variable. So that's why we need to understand how a relation can be represented in the form of a function. When you represent a function with the help of a relation, the relation should be represented at a pair of values, and you should always remember that each input should be mapped with exactly one output. Next form of representation of relation. The another form of representing a relation is a matrix form. So if you could see that when you want to carry anything with respect to the idea of matrix, see, let me take one thing. One is in the form of a set of students as well as set of course matrix. The set of students are Alice, Bob, Claire, Dan, and whose interested courses are CS 101, CS 201, CS 202. And Alice is interested in CS 101 and Bob is interested in CS 201 as well as Dan is also interested. So like this, yeah, data is provided. So is this a relation? Yes, of course, this is a relation. What is a relation? Student course relation, set of students and a set of course. This is a kind of relation. Can I represent this relation as a function? Of course. And one more kind of representation is matrix. So any relation can be represented in the form of a matrix provided you should give value for Mij. I is a corresponding position and j is a corresponding position, right? Alice, which is in the 0th position, can be represented with the 0th position of the course. So 0, 0 like that, right? So it is 1. So this 0, 0 is 1, this 1, 2 is 1, and this 1, 3 is 1, and this 4, 2 is 1, and this 4, 3 is 1, like that, right? So now a relation is represented as an ordered pair A, B, and you can represent them with the help of the value 1, 0, right? So this is how you can represent a relation using matrix. Now, how I can represent a relation using graph? So what is a graph? A graph consists of set of vertices V and a set of edges E. If you have two pair of values A and B, and if it is in the relation, then there is a arrow from A to B, right? So now consider relation A, B such that A divides B. A and B are related to one another, and what type of relation is that A and B is having? A is a number that is divisible by B. When you want to represent these kind of relations using graph, either you can go for bipartite graph or you can go for directed graph. So bipartite graph, you have set of values in one side, another set of values on another side, and it is mapped with one another. This is bipartite in nature. And here it is only directed graph. This is source and this is destination. So source to destination. This is a self loop. A graph, a node in a graph is representing itself. So that is the relation. So how a relations are represented? A representation is made via functions, matrix, as well as graph. Now, binary relation. So what is a binary relation? A relation is said to be a binary relation. Say for example, if you have two things A and B, and two are treated as sets, and you have a specific property between elements x of A and y of B. This property can be described using the ordered pair x, y. So a set of such pairs where x belongs to A and y belongs to B is called a relation, right? You have two things. X and Y ordered pair, and each ordered pair belongs to a certain sets. A is one set and B is another set. If that is the case, then you may treat that as a classical or GRISP, or in general binary relation. So a binary relation is represented in the form of R is equal to X comma Y, such that X belongs to A and Y belongs to B. So this is the idea. What is a Cartesian product? A Cartesian product is nothing but a non-empty subsets. The product set or a Cartesian product A cross B. What is A cross B? Is nothing but A comma B, where A belongs to capital A and B belongs to capital B. Let us take an example. See, I have one set, that is X, that is equal to 2, 4, 6, and another set Y, that is equal to PQR. Now what is the Cartesian product? So 2 into P, 2 into Q, 2 into R, that is one set. Another one is 4 into P, 4 into Q, 4 into R, that is another set. Likewise you have. So now what is the relation? What is the relation? So it is the subset of X star Y. What is the relation? It is. So in order to find out the kind of relation, or you need to find out the idea behind the two entities. So that way you need to find, right? Now what are the operations? So before studying the operations, you should remember about how the operations under classical relations are being studied. You have union operation, you have intersection operation, you have complement, you have containment, and you have identity. If you could see that all these kind of operations involve certain functions. Let me take union function or union S. You have a psi value, and the psi value is utilized with the help of the X comma Y. So when you want to apply this union operation with respect to relation, then you can take maximum value. Likewise for intersection or intersection B, you should take the minimum value of two things. What about the complement? Complement is the negation value, 1 minus that X or Y. What about containment? It is whether it is within that set or not. R is a set, within that you have a yes. What is identity? So pi is equal to pi r or psi equal to er. So this is, you need to understand about the operations of classical relation. So there are 4 major operations: union, intersection, complement, containment, identity. For all cases you should remember, one is maximum operation when you dealt with union, intersection operation when you dealt with minimum, and complement it is negation, and containment and identity are the other related operations. Composition of classical relations. This is very important when respect to binary composition, right? So operations executed on two compatible binary relation. You have a two relation, and these relations are ordered pair, and it is treated as a binary relation. And if you want to do some operation over these two compatible binary relation, to get a single binary relation, you need to do an operation called composition. There are two kinds of composition operation. One is max min composition, another one is max product composition. So max min product composition is denoted as R dot S, and where it has been other value. See, for all Y belongs to capital Y, X R, right, X comma Y, whereas the max product relation is treated as the upper value, right. So this is the value which is taking the max min composition, and this is the value that is taking the max product composition. So this is the idea when you talk about the composition operation with respect to classical relation. So what about this for fuzzy relation? So fuzzy relation is the generalization of the classical relation, and is based on the idea that if you want to relate one event to another event, you may say that it is related or it is not related, but to what extent that fuzzy or that variable is related. So it is defined as a Cartesian product on the classical sets. So you have a set x1, y1, y1, and you have a tuples, Now each tuple may have a different values for the degrees of freedom that has been considered for the membership function, and it should be within the relation. Say for example, see, look at it. If a 0 is there, then I can take x1, x2, x3, x4. So this 0 means that x1 is not related with x2. This 0 represents x1 is not related to x4. So it says whether any relation is there or not. But when you take the other values, those values are between 0 and 1, like 0.2, 0.5, 0.7, 0.8, 0.1 and 0.4. These kind of values are also available in the relation function. But what is the thing that has been happening? See, you are treating this value, that each value is degrees of freedom. Now how to represent this classical relation? See, x1 is mapped to x1, x2 is mapped to x2, x3 is mapped to x3, but what is the weightage associated with the link? 0.2 here, 0.1 here, 0.3 here, 0.7 here. What are all these kind of values? These kind of values are the weightage associated with each links. When you want to associate the weightage, instead of saying presence as well as absence of the link, here you are saying a link is there, but how much weightage I have to give for the link, so that I have to represent. So this is the graphical representation of the link. See, 0.2, 0.3, 0.7, 0.1. So these are all the weightage of the link, and this link size. So either you can represent in the form of a graph or in the form of a matrix. So GRISP relation versus variation. This is GRISP relation. See, it has only the arrowheads and it signifies the directions. Whereas in case of fuzzy relation, in addition to arrowheads, we have the weight values. Weight value. This is fuzzy relation. When you want to represent in the form of matrix, wherever 0 is there is no relation between these two variables. If we are having a non-zero value, then it indicates the kind of thing, but with respect to the other kind of parameters, the 0 represents no connections and some values represents the degree in which the values are related. So this is the difference between GRISP relation as well as fuzzy relation. Right. What are the operations? Again I am repeating: union, intersection, complement, containment, not more than that. Everything falls under these kind of 4 operations. What is this union operation? So you have mu r union s, it means that mu r x comma y and mu s x comma y, you have 2 different values for which you have to take what? Maximum, if it is the union. For mu r intersection s, you have mu r x comma y and mu s x comma y, and the intersection is nothing but the minimum of these 2 values. What is the complement? It is the negation of the value. What is containment? It is checking whether one set is lesser than the other set, or one set seems to be a subset of other set. So these are all the operations that you can perform with the help of the fuzzy relations. What is composition of fuzzy relations? As I said earlier, these are all the very important topic when you want to solve the inference engine framework of fuzzy inference system. Before that, let me discuss about the composition. There are 2 composition, one is max min composition, another one is max product composition. So what is this max min composition, right? So max min composition R is a function in a fuzzy relation in x cross z such that, see, cap and cup for all mu r of x comma y intersection mu r. What about this max min? See, you have to take the max min and you have to take the value, see, max min. So you have to take the minimum of 2 values, mu r of x comma y comma mu s of x comma y. You have to take the minimum of 2 values. From the minimum of 2 values, you have to take the maximum 2 values, that is the thing, that is max product. and another thing the max min. This is the composition of fuzzy relation. Let us explain this with an examples. You have two matrix, one is R matrix, another one is S matrix. The R matrix consists of two rows, right, and three columns, two rows, three columns, whereas S matrix consists of two columns and three rows, right. This is the idea. Now if you want to compute R, yes, maybe by means of max mean as well as max product. So how to calculate it? So given two matrix R and S, and you are asked to calculate max mean as well as max product composition. How to calculate it? What are the expressions that are available? How do you use those expressions to calculate these R dot S, right, max mean composition? See 0.4, 0.5, you need to calculate min of this 0.4, 0.5, comma, min of this 0.6, 0.1, min of this 0 as well as 0. See this value in the row side and this value in the column side. Accordingly, you need to calculate maximum of these things. What is the minimum of these two value? 0.4. What is the minimum of these two value? 0.1. What is the minimum of this value? 0. So next is 0.4, 0.1, 0, and the maximum of these three value is 0.4. So you should break one matrix in the row wise and another matrix in the column wise. Accordingly, you should have it for other. So what are the values obtained? 0.4, this is here, 0.6 and this 0.6 is here, and 0.5, 0.5 is here, and 1 and 1 is here. So this is max mean composition. What is max product composition? Here also you have two matrix, one is a 2 row, 3 columns, another matrix is 3 rows, 2 columns. Now I have to calculate max product, max product of these values, right. So 0.4, 0.5, 0.6, 0.1, 0 into 0, right. For doing the max calculation 0.02, 0.06, 0 is there, and finally 0.06, right. So the product of the values first is taken between the row values and column values. Once the product of the values is calculated, then over the set of the product of the values that has been available, you have to calculate the max value. So this is what max product combination. If you do in the same fashion, you will obtain 0.06, 0.6 and 0.45 and 1. So this is the max. And you please remember that this max mean composition and the max product composition are very much interesting problem and a very much illustrative problem to understand the idea between inference process. So the inference process we will be seeing in the subsequent classes, and for inference process you have three kinds of inference model: Mamdani model, Sugimoto model and Sujino model, and these inference engines will work on this kind of composition, that is max product composition, provided there should be two variables, input and output variable, and that input and output variable can be represented either in the form of a function or in the form of a graph or in the form of a matrix. So if it is represented in the form of a matrix, then you can easily find out the calculation for composition. It should be either max mean composition or max product composition. The final one is tolerance and the equivalence relation. When a relation should be tolerant and when a relation should be equivalence. So this is also draws its idea from classical as well as fuzzy relations. Let me recall the three property: reflexivity property, symmetry property, transitivity property. See, these are the three properties associated with any relation, whether it is classical or fuzzy. Whether it is classical or fuzzy, these properties are the one that characterize the classical as well as fuzzy relation. So reflexivity is said to be in a kind of relation, that means a relation is said to be reflexive if every vertex in the graph originates a single loop. See, for classical we may say that XR, XI, Y, and for fuzzy you have. So here you have mentioned that XR, this is the one, and for this is classical and this is fuzzy. So the notation is very minor change in the form of notation. So when you have a characteristics variable that satisfies all these three characteristics, reflexivity, symmetry, transitivity, when it satisfies all these three things, then that relation is going to be called as equivalence. If it satisfies only the reflexivity and the symmetry property, not the transitivity property, then it is going to be tolerance, right. So this is the thing that you should remember very carefully before proceeding into the idea, right. So what is tolerance and equivalence? These are all the characteristics of classical as well as fuzzy relation. There are three characteristics. One is a reflexivity, another one is symmetry, another one is transitivity. When a relation is said to be transitive in nature, a relation is said to be transitive in nature. Say for example, if you are taking two pairs of edges, take the example of a graph, right, two pairs of edges, and one edge is pointing from one vertex I to another vertex j, that it means that other pointing vertex from vertex j to I and j to k, you have a edge pointing from vertex I to k. So for classical relation, say for example, say psi xi comma xj and psi r xj comma xk, then what is that? You have xr xi comma xk equal to 1. So that way you should understand the difference between the tolerance relation as well as equivalence relation. Okay, with this I come to a topic called fuzzy relation. So in the last class we have discussed about fuzzy sets and operation. There also we have communicated with respect to how a fuzzy set and operation can be compared while you are understanding the idea behind it by means of classical set as well as classical set operations. Likewise, same here, if you have a two ordered set of values, how can they be related with one another? If they are related, how can be represented either in the form of a function or in the form of a matrix or in the form of a. So you should study with the idea that it should be represented in the form of a function or matrix or graph. So when you want to study the classical relations, the classical relation, whatever the theory that is hold good, it is also hold good for the fuzzy relations. The operations that we have discussed in fuzzy operations, so same thing is here when you talk about the idea behind the kind of operation that is needed to solve. So with this I thank for the today for this topic fuzzy relation. We will see the next topic, that is about fuzzy rule based systems, and we will discussing more about this kind of topic. Thank you.